So I'm going to talk about RowHammer, and I'm going to give you a history of it, if you will. This is part of a much longer talk, so I'm going to skip some slides if you don't mind. But feel free to ask any questions. Okay, now that I'm set up, I can go. So basically, RowHammer is the phenomenon that you can predictably induce bit flips in commodity DRAM chips. And more than 80% of the tested DRAM chips at the time we actually did the first studies on it, around 2012, 2013, are vulnerable. I'm going to give you the update from 2020 also. As far as I know, this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. Essentially, these are bit flips. And I believe we should be worried about how we design our AI systems going into the future, because if they're not secure, safe, and reliable, then we may not be able to offload a lot of our decision making to these systems. And it's interesting because folks in the relatively popular literature are writing articles that look like this: forget software, now hackers are exploiting physics. And I think this is a very good characterization at a very high level of RowHammer. So we were very interested in scaling issues in in DRAM for a long time. This is an article that I presented at the International Memory Workshop in 2013. And we argued that scaling is going to be a much bigger problem and reliability is going to become worse in DRAM. And we did a lot of studies related to that. Essentially, we're going to talk about DRAM. Like any other memory, DRAM has a storage device and an access device. Storage device is capacitor, access device is the access transistor, and all of the other peripheral circuitry that makes everything else work. And for DRAM to work, for any memory to work, both of these things should work reliably, of course. But for DRAM, the capacitor must be large enough for reliable sensing, and the access transistor must be large enough for low leakage and high retention time. And ITRS has been predicting for a long time that scaling the DRAM circuitry below some nanometers is challenging. And that was true. And we actually did a lot of studies in terms of reliability of DRAM. This is one example study that we did together with Facebook. We analyzed all of the memory errors that they see in all of their data centers, which is a lot of memory and a lot of servers. And we found out that there's a very strong positive correlation between the chip density that's employed in the server and the server failure rate. And if you're interested, you can read the paper for more detail. And we also did a lot of small scaling studies to understand the errors that happen in DRAM. This is our earliest FPGA infrastructure that we built to test DRAM chips to understand especially retention time related issues. This is another one. And this is where we did a lot of the RowHammer studies actually. And then this is one of the latest versions, which we open sourced recently, and other people in industry and academia are actually using it. And it has a nice interface, much nicer interface with C++ interface. So if people are interested in using it, you can take a look online and we'd be happy to support it. The reason we built these infrastructures was actually a scaling problem, which is the data retention problem in DRAM, which makes it very different from other technologies clearly. And we wanted to understand and overcome this problem. I'm not going to talk about this. I think this is a fascinating issue. And I believe actually data retention errors may be slipping into the field in DRAM today, but we can leave that to the end of the talk. So we did a lot of work on understanding the retention properties of different DRAM cells. How do we actually protect against retention failures, including variable retention time phenomenon, data pattern dependence phenomenon, and many other things, which I'm not going to talk about in this talk. And this work still continues, as you can see, and I'm still fascinated by it. But I'm going to talk about something else we actually also investigated while we were looking at retention errors using our infrastructure. And this is essentially the RowHammer problem. You can predictably induce errors in most DRAM memory chips. And as I said earlier, it's a simple hardware failure mechanism that can create a widespread system security vulnerability. So what's the problem? It's essentially redisturbance. So I don't think there's anything new here in the sense that we know about redisturbance, and any scaled memory technology is going to have some amount of redisturbance. The question is it so bad that should it get exposed to the programs that are running and your data structures get corrupted? And the answer we found out in 2012 was yes. Basically, what is redisturbance in DRAM? In order to read a row in DRAM, you need to activate it, which means that you apply high voltage to that row. In order to read some other row, you need to deactivate this row, which means that you need to apply low voltage, lower the word line, and pre-charge the array. So these are two command pairs, activate and pre-charge. Now, if you keep doing this repeatedly, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, in modern DRAM chips, it turns out you will get errors in physically adjacent rows. And this should not happen clearly because you're not like, touching anything in the physically adjacent rows, and you're not even writing to those rows clearly, right? So this is a redisturbance phenomenon. We call this the hammered row. We call this the victim row. These the victim rows. And we showed that more than 80% of the chips that we tested that belong to 3 major DRAM manufacturers, of which there are only 3, as you probably know, actually exhibit this problem. And this is a scaling problem because the chips that we tested that were manufactured before 2010 actually did not have, were not vulnerable. But the chips that we tested that between 2012 and 2013, all of them were vulnerable. And it's manufacturer independent, as you can see. All of the manufacturer's chips are vulnerable. Basically, at some point, we were able to induce these bit flips with a small enough number of activates that we could fit in a refresh interval. So clearly, if you cannot fit enough activates to cause the bit flips within a refresh interval, the DRAM cells will get refreshed and you will not have this problem. But because of scaling, we could, this phenomenon became so worse that disturbance became so worse that we could do enough activates within a refresh interval. And when we did these studies, we actually used single-sided RowHammer. I will talk about that briefly. And we found out that you needed to do actually about 100,000 plus, 139,000 to be exact, activates and to induce errors, at least at 139,000. Today you can do millions of activates, more than 1 million activates within a refresh interval actually. Okay, keep this in mind because we're going to talk about 2020 where we are. Okay, so this sounds interesting. Clearly it's a reliability problem, but this affects the higher level software. Basically, we also released the software when we wrote this paper. We showed that with 6 instructions, you can induce many errors. Well, so what this simple program, user level program does is it selects addresses X and Y, which map to the same bank, and it basically hammers them, avoiding cache hits, avoiding row hits. It basically does this. And if the chip is vulnerable, you'll get errors. Now, that's not exactly true because this is not the best hammering pattern that you can come up with. It turns out Google later read our paper and came up with a better hammering pattern where they selected X and Y such that they sandwiched one row in between. And they actually were able to show, this is called double-sided row hammering. They were able to show that more chips were vulnerable and you could actually get to the vulnerability much faster. So when we wrote the paper, we observed errors in real systems, Intel and AMD. This is from our paper, and it was validated by many, many folks later on. So I'm not going to spend time on this, but when we wrote the paper, actually, our first sentence was this: memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I still do believe this. I think this is very fundamental for the security and reliability of any system. And we said that you could actually design an attack that would hijack a computer. And while we were actually doing that, the good folks at Google Project Zero published this beautiful blog post, which I recommend you to read, where they showed essentially what we had in mind to do. And this is a copy and paste from their blog post. They said they learned about the problem for our paper, they replicated the problem on a bunch of laptops, and they basically built 2 attacks. One attack is really interesting, which is really at a user level. They were able to flip bits, and they were able to flip the right privilege bits such that they could gain unrestricted access and become root on Linux. The way they were able to do it, I'm not going to go into the detail. It's a beautiful security engineering attack. They were able to induce bit flips in the page table entries of the user level program that's hammering. And these page table entries point to the page tables of this program. And if you actually are able to do that, and if you're careful about how you do that, you can generate a probabilistic attack, and you can gain write access to your own page table by flipping the right bits, let's say the permission bits. And if you gain write access to your own page table, now all bets are off. You can gain any type of access to the entire system. Okay, and this is known as RowHammer vulnerability, and it has many security implications, but that's the core of it basically. I like this nice description from a famous hacker on the internet. It basically says it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. And there's a lot more that I can talk about. In a longer talk, I would talk about some of these really interesting attacks, but I'm not going to do that right now. And this is not an up-to-date list also. I haven't updated this for some time. But you can see that there's a lot of interest in the security community. And these security folks actually came up with very, very creative, clever attacks to take advantage of these bit flips that you can induce in software. And the reason they were able to do that is because you could do this in software. You can induce these bit flips in software. You could reverse engineer all of the mappings that go on from the operating system all the way into the DRAM, and you could take advantage of the bit flips so that you can actually take over the system or get a secret key or You can see many different things over here. As you can see, so these folks, for example, did it with a GPU. These folks did it over a remote direct memory access engine. Basically, once you can actually induce a bit flip reliably, you can take over the system in many different ways. And we've been seeing that essentially. Clearly, there are some solution papers that were also described. So actually, this is the first work that picked up on our work. As you can see, it's MemTest86, the memory testing company that is employed, and the memory testing software that's employed in many systems. And there's a funny story here. Basically, they had to update their web page after they included this RowHammer test in their testing suite. And they had to say the errors detected during this test, albeit exposed only in extreme memory access cases where you're hammering, are most certainly real errors. So they had to tell that to the community, basically. And I'm not going to go into the details of this. So clearly there are many security implications, and there are very interesting ones. I'll basically focus on a couple of these. These folks basically showed that you can gain unrestricted access to the systems of website visitors. These folks show that you could do this on an Android phone with an ARM processor. You could actually download their application, I think, and try and see if your phone is vulnerable. And they actually exploited the deterministic memory access pattern, memory allocation patterns of the Android operating system to fool the operating system to allocate a page table entry to a location that they knew is vulnerable to RowHammer, and then they hammered it so they could actually take over the system deterministically, which is very interesting, clearly. And as I said, you could actually do these attacks much faster using GPUs because you could generate a lot of requests, clearly. You could do this over the network through the remote direct memory access interface. So you could actually hammer a server that's far away from you. And these folks actually did the same thing. And you could actually, this is one of the more recent papers, as you can see over here. Even if you don't gain access, you could actually leak data and you could actually use this as a side channel information. Okay, and there's more. And maybe this is a security implication if you keep getting a lot of bit flips, you may want to get rid of your computer. Of course, that's a joke. Let's talk about solutions a little bit. So clearly, chips out in the field are vulnerable. So we want immediate solutions and we want longer term solutions. I'm going to briefly focus on immediate solutions and then turn into longer term and then talk about the status of RowHammer today. So we propose both types of solutions, and I'm going to briefly talk about Para. It's already employed in the field, although I think DRAM manufacturers, when they decided they wanted to own the solution, Intel turned off some of these solutions, their memory controllers, and we will have a story about that later on. So clearly making DRAM chips is an option, but it comes at a cost. Better isolation, it comes at a cost, and I think this is going to be very difficult. Refreshing frequently is a solution, and you could refresh frequently all across. This is not a good solution clearly, but this is perhaps the only reliable immediate solution we have had. Our paper showed that you need to increase the refresh rates by 7x if you want to actually get rid of all of the bit flips. In the field, I don't think it's 7x right now. Basically, we've closed the vulnerability by refreshing more frequently as an immediate solution, but clearly increasing the refresh rate is something that we don't want to do because as I mentioned, we actually wanted to build this infrastructure to reduce the refresh rates as much as possible and being intelligent about them. Interesting that RowHammer actually leads to increased refresh rates. Sophisticated ECC, I do not believe this is a good solution because we know exactly why these errors are happening, and ECC is a good solution when you have random bit flips. Even though ECC is employed today in DRAM chips internally or at the memory controllers, I don't think spending the ECC budget for RowHammer is a good idea because we can solve the problem in simpler ways. Access counters, keeping track of which rows are being hammered and trying to throttle accesses or not access those rows, etc. I think this is an interesting direction. The difficulty here is cost, power, and complexity, and I think there's some potential over here. We will see how it plays out going into the future. So this was Apple's patch for RowHammer when it was a security vulnerability, and they basically said that they increase the memory refresh rates because that's really the only viable option, in my opinion, in the field. Because our memory controllers are not programmable or changeable in some way. Okay, and other folks in industry released similar patches. I like Apple because they gave credit to our work as well as Google's work before. Okay, our solution was probabilistic. Basically, the idea is very simple. Whenever the memory controller closes a row, it activates adjacent rows, physically adjacent rows with very low probability. And you could set the level of probability depending on your vulnerability to RowHammer and your paranoia, of course, right? And we showed in our paper that if you set the probability to 5 out of 1,000 accesses, you get reliability guarantee that's much better than hard disks. And this is low overhead and low cost and low complexity. The downside is now the memory controller needs to know which rows are physically adjacent. And there's a communication problem that we have today between the memory controller and memory. Memory doesn't want to expose enough to the memory controller such that the memory controller can solve some of these scaling problems much more easily. We can talk about that later on. But this is an effective and low overhead solution to prevent disturbance errors, but we're going to revisit this in 2020. And this is actually the basic idea of Para went into Intel's PTRR mechanism that was implemented inside some memory controllers. Now it's turned off because DRAM manufacturers, as I said, wanted to have the solution to themselves, but you can see in this BIOS, it's not as exactly as we envisioned. It's BIOS programmable over here as opposed to dynamic as we envisioned. But you can pick your RowHammer solution in this Intel processor. You could pick either hardware RowHammer protection or 2x refresh, and hardware RowHammer protection enables you to set the RowHammer activation probability. If you set it to 1 every 2 activations, probably your performance suffers, but if you set it to some other values, your performance will be okay. So, okay, our paper proposed some solutions. We're going to talk about some more, but I think main memory needs some sort of intelligence in the controllers for security. We're going to get back to this. So we've written more papers on RowHammer, and this is a retrospective. If you're really interested, we actually surveyed many papers. We were invited to write this paper for the special issue. This is the state-of-the-art survey in 2019. It goes all the way from security, it goes all the way into the devices and device-level potential solutions and analyses. But let me talk about what has happened in 2020. Basically, we have worked on RowHammer in 2020, at least published the work that we've done in the past. Others have also done it. I'm going to talk about some of the works that we have done. This work is a circuit level work, looks at how the vulnerability is scaling as well as how the mitigation mechanisms have been scaling. This work is something we have collaborated with folks at Kavar Azavi and at Vrije University in Amsterdam to show that existing mitigations that are advertised to be not vulnerable to RowHammer are actually vulnerable to RowHammer, and we're going to talk about this first. And then we also wanted to answer the question, can we actually qualify a memory chip or DRAM chip as not vulnerable to RowHammer? And the answer basically is no, because there is no easy way to create the best possible testing and best possible attack. If there's interest in this, I'd be happy to talk about this later on also. But let me talk about this work. This is actually Trespass work. It was published in Security and Privacy this year. And this is the first work that shows that TRR protected DRAM chips are vulnerable to RowHammer in the field. You don't need to know exactly about what TRR is. This is some mitigation mechanism that's internal to the DRAM chips. All manufacturer has its own version, and it's basically proprietary. They don't disclose any information about how it works. But they advertise it as RowHammer free. Basically, all of the mitigations are advertised as secure, but this work shows that they're not secure. And basically, these TRR mechanisms in general operate by trying to count the number of accesses in some manner to hammered rows, and they issue refreshes to those hammered rows synchronized with the refresh commands in DRAM. What we did in this work was we introduced a many-sided RowHammer attack such that we could bypass these mechanisms. Basically, we hammered many rows to bypass these mitigations by overflowing proprietary TRR tables that detect aggressor rows. And you could do that in many chips, basically. And we partially reverse engineer the mitigation mechanisms implemented in DRAM chips and memory controllers. And we also provide an automatic tool that can effectively create many-sided RowHammer attacks in DDR4 and LPDDR4 chips. You can download this tool. I don't have the link here, but the paper has the link. You can download it and actually improve the tool, make it better, or see if your mechanism your DRAM chips are vulnerable. Although the tool is not it doesn't cover all the cases. Basically, the tool can be improved also. So you can see that by having 5-sided RowHammer, you can induce bit flips in this chip from manufacturer C. By having 8-sided RowHammer, by having 8 rows, 11 rows, and 13 rows, you can induce many bit flips. By having 9-sided RowHammer, by hammering 9 rows, you could actually bypass the mitigation mechanisms, as you can see over here. So the key results is basically we found out that 13 out of 42 tested DDR4 modules are vulnerable from all 3 major manufacturers, and you can see the different types of attacks. And 5 out of 13 mobile phones that we tested are vulnerable from 4 major mobile phone manufacturers. And I believe these results are just scratching the surface because our tool is not exhaustive. There's a lot of room for uncovering more vulnerable chips and phones because RowHammer testing is not a simple problem. Basically, the key takeaways is RowHammer is still an open problem despite the advertisements. And I believe that security by obscurity is not a good solution. And that's the security strategy that's employed by manufacturers today, unfortunately. Okay, let me talk about the other work relatively quickly. This is, here we turned off the mitigation mechanisms in DRAM chips using our infrastructures, FPGA-based infrastructures, and we wanted to understand how the RowHammer vulnerability is scaling at the circuit level. Basically, we characterized more than 1,500 DRAM chips of different DRAM types, technology nodes, and manufacturers. We studied 5 state-of-the-art RowHammer mitigation mechanisms and an ideal mechanism. And we made two major observations. Basically, the first observation is RowHammer is getting much worse at the circuit level. It takes much fewer hammers to induce RowHammer bit flips in newer chips. In some chips, the most scale chips over here, you need only 4,800, basically 4,800 hammers to actually cause bit flips. Remember, this number was 139,000 in 2012 when we did it. Basically, because of circuit scaling, cells are getting too close to each other, and as a result, vulnerability is becoming much worse. And existing mitigation mechanisms do not scale to DRAM chips that are more vulnerable to RowHammer. So if they actually see RowHammer bit flips with 128 hammers, then we get 80% performance loss. I'm going to show you, of course, hopefully we will not get there, or maybe scaling will not continue once we get there. But this is a scaling study, as you could see. It's a more vulnerability modeling study. And basically the conclusion is it's critical to do more research on RowHammer and develop scalable mitigation mechanisms to prevent RowHammer in future systems. So let me give you a very brief overview. I'm not going to go into the details, but we basically built three different infrastructures, DDR3, DDR4, LPDDR4. They're all FPGA based, or in some other ways SoC based. And we were able to study 1,500 plus chips. I'm not going to go into detail. You can see the different types of generations and different nodes over here. Essentially, this is a scaling study to understand how RowHammer is scaling, and this is one result. Basically, you can see over here on the x-axis, we see hammer count, how many times you're hammering rows, and this is the bit flip rate that you get. And DDR4 old generation has a smaller bit flip rate than DDR4 new generation. So you need basically fewer hammer counts to get the same rate of bit flip, as you can see. And at a given hammer count, you get more bit flips. So basically, technology scaling is not working well for RowHammer. RowHammer bit flips rates increase with technology road generation, as you can see over here. This is another study. This is basically how long does it take, how many hammers does it take to actually get the first bit flip. Now you can see that is reducing as technology generation scale. And these are the red bars over here. We have some anomalies over here because we cannot classify the chips really well because the manufacturers don't describe the technology nodes of their chips. This is based on what we have done. We reverse engineer some chips. But you can see that the vulnerability is getting worse. You're getting the same bit flips with fewer hammers. As I said, there are chips whose weakest cells fail only after 4,800 hammers today. Okay, I've already said these key takeaways. I'm not going to go into details, but let's talk about the mitigation mechanisms that were proposed in literature. So this is the number of hammers that are required to induce the first RowHammer bit flip, and this is the normalized system performance provided by the mitigation mechanism. 100 is good. As you get lower, that's bad, basically. So today, we're not terrible with the mitigation mechanisms, assuming they're implemented correctly and securely, of course, which they're not, based on the previous paper. But going forward, things are not scaling very well. Existing mitigation mechanisms actually lead to, there's only one of them that scales, which is the one that I described. But if the RowHammer vulnerability becomes much worse, like 1,000 RowHammers, you're going to lose about 25% of the system performance that you have. That doesn't sound good. Okay, so there's significant opportunity for developing a RowHammer solution with low performance overhead because the ideal mechanism actually scales quite well. You need to go into actually 100 hammers to lose about, let's say, 60% performance over here. Okay, I'm going to skip the slide as I mentioned, but there are promising directions for RowHammer solutions, which I'm not going to talk about. I believe DRAM system cooperation is still promising. Unfortunately, this is not happening as much, and profile guided is very interesting also. So there are more works in 2020 in RowHammer. Micro is coming up. You can see there are two works. One is a solution work, one's an attack work. If you're interested, you can take a look at it. And there was a RowHammer session in security and privacy. And there's another work that talks about actual deep neural networks and their vulnerability to RowHammer in the Usenix Security Symposium. I believe there's more to come. Now let me quickly talk about future memory reliability and security challenges. I think we're going to see more of this basically. DRAM is becoming less reliable, more vulnerable. I believe some other problems may be going unnoticed. Some errors may be slipping into the field. Clearly, redisturb errors slip, and they're still not corrected fully, securely. Retention errors, I believe, are slipping into the field. I'm not going to talk about that. I don't have time. But I believe there may be read errors and write errors that are slipping into the field. And clearly, if exploited, these errors can also pose security vulnerabilities. I believe main memory needs intelligent controllers for security. So how do we keep future memory secure? And there are emerging technologies clearly that have different sorts of vulnerabilities, which I don't have time to also talk about. I believe we need to think about fundamentally secure computing architectures. We want to predict and prevent such. I think of these as safety, security, reliability issues intermingled together, but clearly security can be a concern, but safety is a concern, especially in AI applications, right? So this is a three-step methodology. I'm not going to go into detail. I believe we need to understand the vulnerabilities. We need to predict the vulnerabilities. We need to model them. We need to discover them somehow before they slip into the field. And I think real device data and analysis, like I've been describing, could be very helpful. I believe we need to develop reliable metrics. On top of this, I believe we need to architect in a principled manner. We need to partition the duties across the stack well, not necessarily trust just the DRAM, but actually do the solutions in other parts of the system stack like the memory controller. We cannot give up performance and efficiency. I believe patchability in the field is really important. And I believe design and test, of course, is important. Maybe we need to do more online testing in the memory controller. We need to design for security, and we need to have high coverage and good interaction. So I think clearly understanding and modeling requires real device analysis, and I think Flash is another example where we do this. So when I introduce RowHammer to freshmen, I use this analogy in my class. This is the Galloping Gertie, the Tacoma Narrows Bridge, which essentially had a bit flip, let's say. It's critical infrastructure. It had a bit flip in 1940 and it failed. So this is a safety, reliability, and security problem. So we're building all of this AI infrastructure that's going to do who knows what for our lives. And we're trusting our lives with it. If we get bit flips that are vulnerable, we may have even worse problems that look like this. This is another bridge failure in Seoul on the Han River, and you get fatalities here. This is another one in Minneapolis, and you get fatalities here. This is another one in Genoa, you get fatalities here. I believe we are better than bridges. Clearly, humanity has built bridges for thousands of years. I think computing is softer in the sense that we can patch things better than bridges, perhaps. And I believe in-field patchability can avoid such failures. So let me conclude very quickly. This is my overall summary. Memory reliability is reducing. Reliability issues open up security vulnerabilities, and they're very hard to defend against once they're discovered in the field. RowHammer is a prime example, and I believe it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And its implications on system security research are tremendous and exciting, clearly based on the works that we have seen in security domain. Bad news, RowHammer is getting worse. It's still not fixed, even though there's advertisements saying that it's fixed. But the good news is we have a lot more to do as researchers. We're now fully aware hardware is fallible. We're developing both attacks and solutions, and we're developing hopefully principled models, methodologies, and solutions. So for more on RowHammer, this is the paper that I mentioned earlier, and these are the works that are not covered by paper because they were done in 2020. So at this point, I'll acknowledge people who have funded us. Please keep funding us, and I'll acknowledge students who have clearly contributed to this work. Okay, thank you. I'd be happy to take questions. Oh, that's a great question. I mean, we looked at this in 2014 paper and in the current paper also. So it really depends on, so clearly this is a charge leakage mechanism. So charge cell leaks its charge and you lose charge. As a result, you flip. Now it depends on how you encode the charge. The charge can be encoded as a 1 or a 0. And this very much depends on the DRAM manufacturer and how they encode the charge, essentially. So we saw, in some manufacturers, we saw 50-50, I believe, between 1 to 0, 0 to 1. In some manufacturers, we saw an overwhelming majority flipping from 1 to 0 and very few flipping from 0 to 1. Sure. 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 Yeah, that's a great question. I mean, I'm not sure. In the end, I saw exactly what you showed. So I think I felt it was more like a marketing statement, clearly. But I think, I mean, RowHammer, Redisturb exists in all technologies. Clearly, SRAM has it. Hard disks have it, right? In some technologies, they're more severe than others. I believe as technology scales, we will see these issues. Some technologies may have write disturb issues. Maybe they don't have read disturb issues as bad. So I believe it really depends. We need to study the technologies and understand these vulnerabilities. We cannot, without studying, I think we cannot really make a statement fully. For example, in our studies with phase change memory, we did see some read disturb issues, but maybe write disturb can be worse in phase change memory. We'll have to see. Again, it really depends on devices, and it also depends on the technology nodes. DRAM at some point scaled to smaller technology nodes that we saw it, and maybe some of those other technologies have not scaled to the technology nodes where we see the issues yet, right?